So these notes go with the 1.9 Ready, Set, Go. And we're going to take a look at some strategies for finding some missing terms in an arithmetic sequence. So when it says arithmetic, that means that there's an adding or a subtracting pattern between the terms. So let's go ahead and look at the first term, which is a 3. And then the next term is missing. But I know that for an adding pattern, to get from one term to the next, you would add or subtract a D. I'm going to call D for common difference. How do I know if it's add or subtract? Well, I notice that the fourth term is bigger. So this definitely has to be an adding pattern, plus D. And then if I add D one more time, I'm going to get to 18. So with an arithmetic sequence, to get from one term, the previous term, to the next term, you're going to add a common difference, add a common difference, and then add the last common difference and get to 18. If this number here was smaller than my first term, then I would have subtracted. And I'm going to call it D, D, D because it's the same number being added over and over. Okay, that's what an arithmetic sequence is. That's the pattern. So my first term was 3, and then I added a D, and I added a D, and I added a D, and that takes me to 18. Okay, so what some students like to do is kind of figure out what the number was with some guessing and checking. Okay, and I know here that all of these common differences, to get from 3 all the way to 18, 18 minus 3 makes 15. Those 3 common differences must be 15. 3 plus 15 takes you to 18. So if each of these D's were the same, I think the common difference, which I'm calling D, must be a 5. Does that work? Let's test out my pattern. 3 plus 5 makes 8. 8 plus 5 makes 13. 13 plus 5, yeah, the common difference must be a 5 each time. Okay, and then what is my strategy? Okay, it's not enough just to say that I'm guessing. Okay, so my strategy was, okay, my reasoning, my justification was, I subtracted to find the difference between the final term and my initial term, to find the difference between the two terms. And then I knew that there must be 3 common differences. Okay, I knew there was 3 common differences. There was 3 common differences added. So each one must be 5. So each D equals 5. Why did I call the common difference D? D stands for difference. Okay, so when you have an arithmetic sequence, what are the things that are going to happen? Okay, arithmetic sequences have a starting value. They have a starting value, okay, and then they also have a common difference. A common difference, okay, between the terms. A common difference between the terms. And that means something's being added or subtracted. Okay, for example, we could have D equal a positive 7, or we could have the common difference equal negative 11 if the numbers are going down. Okay, what do geometric sequences have? Well, they definitely have a starting value. They have a starting value, okay, but they don't have a common difference. They have a common ratio, between the terms, okay? And so I'm going to call that an R. For example, if the pattern is times by 2, then R equals 2. Okay, and then I'm going to put a star by this one. If the difference is divide by 4, then I'll say 1/4. Okay, so that means divide by 4. Each term gets the common difference or the common ratio. So if you have 3 D's, then you have 3 common differences to get you there. Okay, and then neither, sometimes it could be neither, it would have a starting value, and then, okay, there is not a consistent pattern. Not a consistent pattern between the terms. So maybe it's add 2, add 2, add 2, but then it's suddenly add 5, okay? That's not arithmetic. And if it was times 2, times 2, times 2, and then times 5, that is not a consistent pattern. So consistent pattern means the same. Every term gets the same. So if that happens, then you would pick neither. Okay, let's determine if these sequences of numbers down here are either arithmetic, geometric, or neither. And then we'll write some equations. Okay, but if it's neither, then we don't write the equations. Okay, if it's neither, we don't write any equations for it. Okay, so let's take a look at this pattern. I see here that this is plus 6, and then from 9 to 14, it's add 5. Wait a minute, that's not consistent. Okay, so this is not arithmetic. Oh, maybe it's geometric. Let's see, 3 times 3 is 9. Is 9 times 3 14? No, okay, it's not geometric either. So this is a nice list of numbers, but this is neither arithmetic nor is it geometric. Okay, so I cannot write equations for something that's not a consistent pattern. Okay, let's take a look at the next one. 2, 4, 7, 10. They're going up. So it's either add or multiply. Okay, let's see. Is it multiply? Is it times 2? Times 2? No, that did not work. Let's see. Is it add? This is plus 3. Plus 3. Okay, so the question is this also plus 3? And the answer is yes. Okay, this is a consistent pattern. The pattern is adding 3, so I'm going to say it's arithmetic. Okay, people are doing a good job with recursive. Okay, recursive means previous, uses the previous. So I'm going to write an equation for f of n, any term using the previous. So if this is n, right before n comes n minus 1. So you take the f of n To find that term, you use the previous term, f of n minus 1, and the pattern is add 3. This right here is previous. Take the previous term, take the previous output, and add 3. But remember, with recursive, you always have to say how this pattern starts. So I'm going to say that the first term right there, the first term is 2. Okay. To do the explicit, we really have to notice the pattern. Okay, we have to notice the pattern of what's happening. Some people like to see this in chart form. So if we have the first term is 2, the second one is 4, the third term is 7, what's happening here? Okay, the explicit formula always says, start with the first one. So the first term is 2. The second term was 2 plus a 3. The third term was 2 plus a 3 plus a 3. So if I want to get all the way down to the nth term, I would say start with 2, and then I'd have to add on some 3's. Now how many 3's is each one going to get? The first term got 0. The second term got 1. The third term only got 2. Is that equal? No, it seems like it's 1 less. So n is not going to get n, but rather n minus 1. All right, we have one more example here. I notice that the pattern is increasing. So the question is it being added or multiplied or neither? Is this plus 2? Well, this is not plus 2. Let's try times by 2. Times by 2, is this one also times by 2? Yes. Multiply by 2 means the pattern is geometric. Okay. What's the recursive equation? F of n equals the previous term, f of n minus 1, and the pattern is multiply by 2. Don't forget, with recursive, you have to tell me how it starts. F of 1, the first term was equal to a 2. Okay. And then for the explicit equation, we're going to say f of n equals, okay, the starting number. So the starting number was 2. And then the pattern is multiply by 2. So we have to multiply by 2, but the question is how many times? How many times? So when you start with 1, we had no additional 2's. Then we had 4, 8, so this was 2, and then multiplied by 2 one time. The starting number 2, and then it got 2 2's. So is n going to get n? So if we jump down here, n, to do f of n, we'd start with a 2, and how many 2's would we need? To the power of n minus 1, 1 less, multiply by 2. I hope this helps you with your ready, set, go.